name is Beyza Yaman. I am a postdoctoral research fellow in Adapt Center at Dublin City University. Today I'm going to talk to you about my project called LinkedDataOps, Geospatial linked data operations based on quality process cycle. Geospatial data suffers from quality problems. The inaccuracies in geospatial data can cause major problems in real life, such as accidental bombing of Chinese embassy in Belgrade or the Irish Coast Guard helicopter crash. On the other hand, there are very little work on the quality assessment of geospatial linked data. As you might know, DevOps is a set of continuous practices to improve the quality of software. As it is for software, DataOps is a methodology to improve the quality of data and reduce the time of data analytics for the data pipelines. So in this project, we propose linked DataOps approach to improve the quality of linked data processing steps for the entire linked data lifecycle. In this study, we are collaborating with Ordnance Survey Ireland, which is a national mapping agency of Ireland. In this figure, you could see the end-to-end data quality workflow. The data is first captured through the surveying. Here, as you can see, through surveying the land using airplanes, which were adjusted by people if necessary and then digitalized to computers. After going through some transforming phases from GMS to prime to a database, from prime to database to MRDS data warehouse, and then the last steps as online stores or linked data or job portal. After going these through some transforming phases, the data is then provided in different formats, openly or with a host. Each step introduces data quality problems to the organizations, in this case for OSI. But the data quality throughout the data pipeline and lifecycle is key to OSI, because high quality leads to better governance in the organization. On the other hand, OSI has to provide continuous upward reporting to the Irish government, European Commission, or United Nations, and provide feedback to managers within OSI for engineering team for the quality of data. So, because of these reasons, it is important to conform to the standards for the better governance. And there are several standards proposed for the quality of geospatial data, such as United Nations Global Geospatial Information Management Framework, or ISO standards, or Open Geospatial Consortium standards, or W3C Spatial Data on the Web best practices. And they all provide requirements to publish the data set and metadata in the best way. This is our system architecture that we are applying. And starting from the data publishing pipeline, as we mentioned in the previous slides, we created standards-based metrics based on existing approaches, such as ISO, W3C, or OGC. And we assess the geospatial data by using an open source framework called DCU. On the other hand, we uplift the existing data quality results, which was provided by one spatial data, to a semantic layer to have a unified quality graph, as you see in the third layer. In this layer also we provide the created data catalog with data quality, data lineage, and data names for the effective data governance. and we provide them with different standards by mapping these standards to each other. And on the and finally, we provide end-to-end data quality dashboard to provide standardized reports. And this allows the OSI to have a bigger overview of evolving data with standards-based assessments, visualization, and standards conformance and quality reporting of the data. In the slide, you could see the identified priority standards compliance points. We identified a list of geospatial data standards conformance points or best practice recommendations. You could see in the slide the requirement descriptions where it is originated from, either from OGC or W3C or ISO. We use 3 standardization approaches, as you might see here. It was most essential and crucial to enable publication of associated data in line with agreed standards. In accordance with OSI staff, most essential metrics were chosen to check the usage of chosen standards, to reduce the heterogeneity in representing data, to measure the discoverability and freshness of the data, and to see the impact on the usage by the link open data cloud users. And the third reason was to measure the consistency of data to provide high uniformity. And for the last, we wanted to measure the completeness of data to provide high coverage to the users. So we created a sort of new quality metrics for automated data assessment in a quality framework called LUSU. And due to restrictions, now I'm not going to explain all of them, but I'm going to show a specific examples from these metrics. This polygon and multi-polygon check. One of the requirements is polygons and multi-polygons shall form a closed circuit. So in this metric, we are looking at the rate of special correctly described polygon and multi-polygons that the data set covers. So you could see an example of polygon representation here for the linked data. So this is an ITM standard. As we see, the starting point and the finishing point of polygon should form a closed circuit, as you see here. So this is relevant for the boundaries data. So we are looking at the starting point and end point of a polygon, and if this if they are both equal to each other, then our polygon is correctly represented. So this allows us to represent spatial data in a way that matches the needs of target audiences. In this work, we assess the quality of several data sets published openly in the linked open data cloud. As you can see, the metric values shown are the average value of metric for all geospatial linked data sources in the data sets. The table also shows mean observed values of each metric across all data sets and the mean of all metrics for each data sets as simply aggregated quality indicator. In general, we see that most data sets either conform or do not conform to specific standards, which we have as like results 1 or 0. Nonetheless, the aggregated metric value gives an insight into overall level of standards compliance for specific data sets. However, choice of which metrics are relevant for a specific application or dataset is always a key quality management decision. It can be said that OSI have selected these metrics as important for their datasets, and thus these metrics help OSI monitor quality and standards. It is interesting to note that sub-datasets such as OSI parishes sample can have quite different quality metric scores than their parent dataset. This is partially due to the scale and complexity of national spatial data collection, which is an ongoing task with evolving requirements, methods, and teams contributing to maintaining an overall dataset composed of many contributions over time. On the other hand, these results also show us the adoption of non-standard vocabularies decreases the scores. Overall, the aggregated metric values are in the mid-range for most datasets, showing that usage of geospatial linked data standards and best practices are not widely applied by the publishers yet. And this is the other approach that we apply, uplifting the traditional data quality outputs to RDF-based data quality results to have a unified knowledge graph of data quality results. So starting from the traditional data, we would have the results for also linked data, and we would have an end-to-end quality results for this pipeline. So in this approach, we had bulk validation table with details such as what rule set was executed, the start and date of assessment, and the count of features processed per class, and it provides assessment session metadata. On the other hand, we had a validation table storing the records of each invalid feature in prime2 datasets, what kind of validation rule the feature failed, and the geometry and hotspot of a failing feature. So we applied our TRML tools to these tables, and we uplifted the information existing in this table to a graph shape model. By using schema and quality metadata observations, we published the quality metadata observations and quality problem report for the existing problems in the data. And this is our end-to-end data quality dashboard to publish the data quality results and enable reporting for the data quality assessment. This enables the tracking of data quality for OSI data pipeline over time, as well as showing a unified view of quality dimensions using ISO 19157 versus linked data, and for viewing these individual quality dimensions over time. The data quality analysis page is divided into three parts: a bar chart showing the data quality over time of the pipeline nodes, a second bar chart showing the quality dimensions of pipeline nodes, and a navigation bar on the left with the slider for changing standards and checkboxes for selecting and deselecting dimensions. The toggle can be clicked to swap between quality standards and quality dimensions. Bar chart reflects these changes. The quality over time bar chart can also change to show individual dimensions by selecting checkboxes in the navigation bar. And this model allows us to match end-to-end data lineage. And the OSI business data lineage view of the data pipeline model defines a structure to describe the datasets, such as GMS, Prime2, MRDS, and linked data, and subdatasets such as buildings, core or national MRDS or Galway buildings data. Throughout the metadata vocabularies. The metadata information is described based on the W3C standards such as DCAT, Pro, Ontology, DQV, and United Nations DGIM data teams. The DCAT teams from the list provided in the UNGGIM for each datasets and subdatasets respectively. The was right from property from the Pro ontology defines a dataset or subdataset as the result of derivation or a transformation from a pre-existing source dataset or subdataset. This is a small snippet for the data lineage. Here, as you can see, we show the generic information such as title or description. We also use the cat information for the data catalog, such as the sub data sets of existing data set using dcat as part. On the other hand, we show the standards conformance information by the DCT conforms to property. And we also show provenance information pro by Pro ontology and DCT Dublin Core Terms ontology. And we also show quality measures by using DQV vocabulary and data teams information. And this is the page for data lineage results. We are able to show, so this page presents the reporting features based on the OSI data catalog, which is connected with data team, provenance, and data quality metadata. The dashboard page has several filters on the left side of the page, which allows users to click interactively. Users can pose various queries with different views by clicking on the filters and visualize the datasets relations semantically. We have seen that it is not trivial to implement an effective data quality dashboard, but this is an ongoing phase collaboratively with the industry. But this allows OSI to enable team and standards-based visualization approaches and new standards-based assessment for the datasets. On the other hand, geospatial data and the load cloud still need standards translation, and still there's a long way to go with respect to the conforming to the standards. But there's a potential for semantic modeling of data quality standards in this area. And there's a need for ongoing collaboration in the industry for effective data quality dashboard. And we are also organizing a workshop in the fourth international, which is called Fourth International Workshop on Geospatial Linked Data, collocated with ESWC 2021. And we are expecting to see you there. And we are editing a journal called ISPRS International Journal of Geoinformation with a special issue called a Semantic Special Web. And we are looking for your submissions for this journal as well. So thank you very much for listening, and if you have any question, please contact me from this email.